Algebra 1, Lecture 7. At Lehman, at CUNY, there are 28 classes in a semester. So this is the 7th, so we're a quarter of the way through. And the midterm is on the 14th class, so that's exactly the middle of the term. And what we're studying now is derivatives and rules for differentiating. So, and we're also studying particular functions and their derivatives. So we have the addition rule, the product rule, the quotient rule. The product and the quotient rules are both worth repeating. So the product rule says that you have two functions, f and x, f and g. The derivative with respect to x of f of x times g of x is the derivative of the first function times the second plus the first function times the derivative of the second. And again, we're using here two different notations for the derivative, but it's the same derivative. That's the product rule. So for example, if we have the function x cosine x, and we want to differentiate that, that's a product of two functions whose derivatives we know. That's the derivative with respect to x of x times the cosine plus x times the derivative of the cosine. The derivative of x is 1. And the derivative of the cosine is minus the sine. So it's x times minus the sine of x. So that's the derivative of x cosine x. Any question about that? The quotient rule, which is a little bit more complicated, says if you have f of x divided by g of x, if you have a quotient of two functions, and the denominator is not 0, the derivative of the quotient is against a quotient whose denominator is the original quotient, g of x, the original denominator squared. And in the numerator, we have the derivative of f times g minus f times the derivative of g. So for example, if we have the function x over cosine x, and we want to differentiate that, the denominator will be cosine squared x, that's squared. And that's the derivative of x, which is 1 times the cosine minus x times the derivative of the cosine, which is minus the sine. Minus times minus is plus. So we get this. So as a nice example, I'll pick one which is in the text. Suppose we have the function f of x, which is a rational function, x squared plus 1 over x squared minus 4, and we want to find the tangent line. We want to calculate the tangent line at the point 3, 2. And what does 3, 2 mean? It's like, this means, this claims that this curve, whatever it looks like, goes through the point 3, 2. And in fact, what is f of 3? F of 3 is 3 squared plus 1 over 3 squared minus 4. 3 squared is 9 plus 1 is 10. 9 minus 4 is 5. 10 over 5 is 2. So f of 3 is equal to 2. So this point (3, 2) does lie on the curve. In fact, I'll do this in a moment with Maple, but just to see how to try to sketch this by hand. If you look at this function, this is 0 when x is plus 2, or the denominator is 0 at 2 and minus 2. So that means that this function has vertical asymptotes at 2 and minus 2. And when x is bigger than 2, the denominator is positive. So this function is positive, it's above the x-axis. As x goes to infinity or to minus infinity, this function is approaching 1. So this has a horizontal asymptote at 1, has vertical asymptotes at 2 and minus 2. And this function is always positive. The graph here is going to look something like this. And we're interested in the tangent line through the graph at this point. Let's see. When x is between minus 2 and plus 2, this denominator is always positive, but when x is between minus 2 and plus 2, this is negative. So this is going to be negative below the x-axis between minus 2 and plus 2. When x equals 0, it's minus a fourth, and it's going to look something like this here. But I'm interested in the tangent line at this point, 3, 2 on the curve. And the tangent line, so you have to know the equation of the tangent line to a curve at a point. It's y equals what? The derivative of the function at the point 3 times x minus 3 plus the value of the function at 3. So the value of the function is 3 is 2. What's the derivative of the function at 3? So I need to take my function and differentiate it. So let me do it right here. I want to find f prime of x. That's the derivative with respect to x of this quotient, x squared plus 1 over x squared minus 4. So that's the denominator squared. And in the numerator is the derivative of the numerator of the function. The derivative of x squared plus 1 is 2x times the denominator minus the numerator times the derivative of the denominator. Right. Any questions at this point? I mean, this is the kind of calculation you have to learn how to do correctly. And
Professor,
yes, sir.
I have a question. For the graph, how did you find the asymptotes?
Well, so this is my function. F of x equals x squared plus 1 over x squared minus 4. And we know they're vertical asymptotes where the denominator x squared minus 4, that's the denominator, is 0, which means x equals plus or minus 2. So this is the line x equal 2, and this vertical line is x equal minus 2. And we have a horizontal asymptote that means what happens as x goes to infinity for this function f of x. And when you have a rational function where the numerator and denominator have the same degree, the limit as x goes to actually plus or minus infinity. It's just the ratio of the coefficients of the leading terms. 1 over 1 is 1. So that says that this horizontal line, y equals plus 1, y equals 1. That's a horizontal asymptote. That's where the asymptotes come from. Other questions about that? Anything that I need to explain more? All right. So I need to find the value of the derivative of the function when x is 3. So this is my function, it's a quotient. I use the quotient rule to find the derivative. So this numerator is 2x cubed minus 8x minus 2x cubed minus 2x. So it looks like I get minus 12x over x squared minus 4 squared. So if I evaluate this at 3, I get minus 12 times 3, which is 36. 3 squared is 9 minus 4 is 5. 5 squared is 25. So that looks like oops, sorry. 8 minus 2 is 10. Might as well do arithmetic correctly. So when x is 3, that's minus 30, which is minus 6 over 5. So that's the value of the derivative of the function at 3. So here is the equation of the tangent line. Y equals the derivative minus 6/5 times x minus 3 plus the value of the function at 3, which is 2. So this is minus 6/5 x minus 6/5 times minus 3 is plus 18 over 5 plus 2. So 18 over 5 plus 2 is 18 plus 10 over 5 plus 28 over 5. So that's the tangent line. Okay. And you can do it very nicely by hand, and you have a very good idea of what it looks like. But of course, if you're interested in seeing it done precisely, we have the advantage of Calculus Lab. And I don't know, not every teacher uses the same program in the Calc Lab, but the best program, I believe, is Maple. And so let's see what Maple would give us for this. So let me try and switch so I can share the screen with the Maple worksheet. Okay. So here's a Maple worksheet. Can someone tell me if you can see this on your screens? Is this visible?
Yeah, we could see it.
Okay. So I have the function f equals x goes to, what is my function? X squared plus 1 divided by x squared minus 4. And in particular, if I evaluate f at 3, I get 2. And the derivative of f, oops, should be a lowercase. What am I doing there? Derivative of Maple is case sensitive. It's equal to that. So if I take the derivative of f, evaluated at the point 3, I get minus 6/5. So my tangent line, I can call it anything I like, but I'll just call it tangent line today. The tangent line is the derivative of f evaluated at 3 times x minus 3. I'm just using the formula for the tangent line, just to show you that you get the right thing. That's exactly what we got. So if I want to plot two things on the same curve, so when I'm plotting two functions, I have to put them in curly brackets. One of the functions is f of x, and the other is tangent line, curly bracket, x. I'll modify this in a moment, but let's see what we get. Oh, wow. Looks pretty good. Actually, it's just the kind of picture that I drew. But you'll notice this is not drawn to scale. So 5 units vertically is just this small amount. 5 units horizontally is much bigger. If I want it drawn to scale, I don't always want to do that, but it's useful sometimes. I right click and click on scaling constraint, and now it's drawn to scale. So this is exactly what this looks like. Yeah, exactly what it looks like. Very pretty. So here's the red. That's the curve. And you see there's a vertical asymptote at +2 and -2. And there's a horizontal asymptote at 1. Let me just put in the horizontal line. If I put in the constant function 1, that actually, now this red line is the horizontal asymptote. And the green line is the tangent line. Okay. Really is very pretty. It's quite amazing what Maple can do with just a few simple commands. Okay. So let me stop the share. And we should be back on the screen. The other thing we worked out last week were the trigonometric integrals. The two basic ones are the sine and the cosine. And these are the rules you should always remember. The derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. And from these, we can calculate the derivatives of the other 6 trig functions. For example, what's the derivative of the tangent? Well, the tangent is sine over cosine. And we can use the quotient rule to find this. Cosine x, in the derivative, we square it. And it's the derivative of the sine, times, which is the cosine, times the cosine, minus the sine times the derivative of the cosine, which is minus the sine. You put this together, I have cosine squared x, minus times minus is plus sine squared x over cosine squared x. But the basic trig identity is that cosine squared plus sine squared is 1. So this is 1 over cosine squared x, or 1 over the cosine of x all squared, and 1 over the cosine is the definition of the secant. So the derivative of the tangent is secant squared. Okay. Any questions about this? Let's do another one. Suppose we want the derivative of the cosecant. So you have to remember that cosecant is defined to be 1 over the sine. And I can compute this with the quotient rule. So I square the denominator. And then in the numerator, we get the derivative of 1, which is 0, times the denominator, minus 1 times the derivative of the denominator, minus cosine x. So that's minus cosine x over sine squared x. Or if you like, you can write this as minus cosine x over sine x times 1 over sine x. Cosine times sine is sine squared. Cosine over sine is the cotangent of x, and 1 over the sine is the cosecant of x. So the derivative of the cosecant is is minus the cotangent times the cosecant. Now, You know, we have what are sometimes called higher order derivatives. If you have a function f of x, if you differentiate it, you get f prime of x. But that's just another function. You can differentiate it again, and you get what is called, so the derivative with respect to x of the first derivative of x is the second derivative of x, which we sometimes write as like f double prime of x. And if we differentiate that again, we get the third derivative. Of course, you might not write it like all these little marks. You can sometimes write f. Let's write the 3 and it's a superscript. This just means the third derivative. And it's even worse if you keep with the primes. If you wanted the fourth derivative, you'd have to write something like that, which looks terrible. So, but this means the fourth derivative. And in general, for all n greater than or equal to 1, the nth derivative of x is the function obtained simply by differentiating f of x n times. So you have a function, you differentiate it, you get another function. And if you're lucky, you can find its derivative. Let's look at an example. Suppose f of x is sine x. The first derivative is cosine x. The second derivative, you differentiate the cosine, you get minus the sine. The third derivative, if you differentiate minus the sine, you get minus the cosine, because the derivative of sine is cosine. The derivative of minus the cosine is minus sine x, which is plus sine x. You can actually see you're back to where you started. If you differentiate the sine 4 times, you get back the sine. So this repeats cyclically. The fifth derivative is the derivative of the sine, which is the cosine. The sixth derivative is minus the sine. The seventh derivative is minus the cosine. The eighth derivative is the sine again, right? Every 4 derivatives, this repeats. Like the first derivative is the fifth derivative. The fifth derivative would be the ninth derivative. And so on. Okay. Okay. So that's all. Higher derivative simply means differentiate over and over and over again. No. So let's just review 2 things, or interpretations of the derivative of a function. That is, if you have a function f of x and you compute the derivative, what does it mean? So we have seen one geometrical interpretation. If you have a function, let's say this is the graph of y equals f of x, and you take a point on the graph, let's say this is a, and on the graph, this is a f of a. You take the tangent line to the curve at that point. The derivative of the function at this point a is the slope of the tangent line. to the curve y equals f of x at the point a comma f of a, right? At this point on the graph, if you make a linear approximation to the function, that's a straight line, and the line that's the best approximation to your function around this point is the tangent to the curve at the point. And when you try to figure out what the slope of such a line would be, that leads immediately to the definition of the derivative. So this is a kind of geometrical definition. And a physical definition is in terms of velocity, the rate at which something is moving. So we have the idea of the derivative as velocity. And let's suppose that, let's think of the variable t as time, and s equal f of t. You have a function f of t is the position of a particle moving in a fixed direction at time t. So if you were to graph this, this is time t, this is the position. Your particle, this tells you a time at any given time where the particle is located. And this leads immediately to the derivative of, again, suppose at some time a, the particle is at position s of a. We want to know what's the speed. So what one does is take some small interval of time. Let's say this is a. Let's say this is a plus some delta t. So in this time interval from a to a plus delta t, the amount the particle has moved is s of t plus delta t from its position at time t, s of t. So minus s, sorry, s of a plus delta t minus s of a. So in this time interval, the position has moved this amount. So this distance divided by the amount of time it took to get there, that's your average velocity over this time interval. And if you want the instantaneous velocity, you take this limit as this delta t goes to 0. And if that exists, it should be an f. This is f prime at t. So the physical interpretation of the derivative is, if you have a function f of t and s is the position at time t, then the velocity v is equal to the derivative at time t. All right. That's velocity. This can be positive or negative. If it's positive, that means you're going forward. If it's negative, you're going backward. The speed is the absolute value of velocity. So velocity has a direction to the right or to the left. Speed is non-negative. So the speedometer in your car gives you your speed. It doesn't tell you which direction you're going in. It just tells you how fast you're going. Okay. And you will have in your exercises a lot of examples using related, they're all essentially the same. They're all exactly the same mathematically, but there are various interpretations of the derivative in geometry and physics and economics and epidemiology. You want to know how fast the disease is spreading and so forth. Okay. But I want to get back to rules for calculating the derivative. And the most fundamental rule, we need all the rules we've learned so far, but the most fundamental rule in some sense is the chain rule. And the chain rule gives us the derivative of what's called a composite function. So the idea of a composite function is the following. Suppose you have some function g, which takes a number x to the number g of x. And suppose you have another function f, which takes a number, let's say u, to the number f of u. Now, if you put these two together, you would have x goes to g of x, and then when you apply f to g of x, you get f of g of x. So that's one function from x from here over to here, and this is what is called a composite function. You're putting these two functions together. And the chain rule, and we write this, well, all right. So if you have this composite function, f of g of x, we want to know what is the derivative of this. I mean, just to indicate that this can be a little bit complicated, more complicated than you think. Suppose g of x is x squared. That's a simple function. We know the derivative. The derivative is g prime of x. Suppose we have a function f of u equals sine u. We know the derivative of the sine is the cosine. But if you take the composite function f of g of x, that's equal to the sine of x squared. And that derivative is something new for us. That's something we haven't seen yet, and maybe a little bit hard to calculate.
Great.
But we have a rule for so this is a composite function. The sine of x squared is the composite of the function x squared with the function sine u. And the chain rule says the following: the derivative of f composed with g is f prime. So we think of u equals g of x and y equals f of u. So it's f prime of u times g prime of x. It's almost the product of the derivatives, but it's f prime, the derivative of f, but evaluated at g of x times g prime of x. So a symbolic way of writing this is, so y is f of g of x. So this is dy dx. F prime of u is dy du. G prime of x is the derivative of g of x is u, du dx. Now, this almost looks correct if these were fractions. This is like, if these were fractions, dy, du, dx, you would cancel the du's and get dy, dx. But of course, and that's nonsense. These aren't fractions. These actually these are derivatives. But the notation is beautifully suggestive of what the chain rule really is. So let's apply this to the composite function, the one we just started with. Say u is x squared. That's my function g of x. Y is the sine of u. That's my function f of u. And f composed with g of x is equal to the sine of x squared. Now we know these derivatives. G prime of x, the derivative of x squared is 2x. F prime of u, the derivative of the sine of u, is the cosine of u. So if we use this formula, the derivative with respect to x of the sine of x squared, that's the derivative with respect to x of f of g of x. That's f prime of u, g prime of x. F prime of u is the cosine of u, g prime of x is 2x. So that's almost the answer, but we want the answer in terms of x. So we want to replace u by something in terms of x, but u is x squared. So this is, let me write the 2x in front, 2x times the cosine of x squared. And that's the answer. The derivative of the sine of x squared is 2x times the cosine of x squared. So we need to pause for a moment so you have a chance to take a look at this and try to disentangle the algebra. I mean, again, the only way to learn this is to learn by doing. So let me just write down the chain rule, and I'm going to compute a number of examples. So the derivative with respect to x of f of g of x is f prime of u, which is g of x, g prime of x. That's the chain rule. Or symbolically, dy dx is dy du du dx. So suppose we have y is equal to 5x plus 4 to the 3 halves. And we want to find dy dx. So you have to look at this and see whether this is the composite of two functions that are easy to differentiate. Well, so this is like u to the 3 halves, where u is 5x plus 4, right? So this is of the form something to the 3 halves power, and the something is 5x plus 4. So I can call this my function g of x, and my function f of u, that can be u to the 3 halves. Because if I define f and g like this, f of g of x is f of 5x plus 4, and f takes its argument and raises it to the 3 halves power. So this dy dx is the derivative with respect to x of f of g of x. Now, the hard thing, the skill you have to learn is how to do this decomposition, to look at this and see how to decompose it into the composite of two functions. And the chain rule says this is f prime at g of x, g prime of x. But for these functions, it's easy to figure out the derivatives. If f of u is u to the 3 halves by the power rule, f prime of u is 3 halves u to the 3 halves minus 1, or a half. G of x is 5x plus 4, that's even easier. G prime of x is 5. So this is equal to f prime at g of x. F prime is this, so that's 3 halves g of x to the 1 half times g prime of x times 5. So 5 times 3 halves is 15 halves times g of x to the 1 half g of x is 5x plus 5, 5x plus 4, raised to the 1 half power, or the square root. So that's the answer. Let's look at another example. Suppose y is 6x cubed plus 3x plus 1 to the 10th power. So this is like f of g of x for g of x equal to 6x cubed plus 3x plus 1. And we're raising that to the 10th power. So we have the function f of u, which is u to the 10th. So if we let g of x be 6x cubed plus 3x plus 1, and f of u be u to the 10th, we've decomposed this into the composite of two simple functions. If g of x is this cubic polynomial, g prime of x is 18x squared plus 3, and f prime of u, the derivative of u to the 10th, is 10 u to the 9th. So dy dx is f prime of g of x, g prime of x. So f prime is 10 g of x to the 9th times g prime of x times 18 x squared plus 3. G of x was 6x cubed plus 3x plus 1. So this is 10, 6x cubed plus 3x plus 1 times to the 9th. Right? 10 g of x to the 9th times g prime of x, which is 18 x squared plus 3. You want to factor a 3 out of this, you will get 30 times 6x squared plus 1 times 6x cubed plus 3x plus 1 to the 9th. Just another way of writing the same thing. All right. Any questions about this? Let's keep doing some examples. That's the only way to really see what's going on. Suppose I have the function y is the square root of 5x squared plus 1. So if I were to let g of x be equal to 5x squared plus 1, this will be the square root of g of x. Now, if I were to let f of u be the square root of u, this is f of g of x. So here I've decomposed this function into the composite of two simpler functions, a polynomial and square root. G prime of x is just 10x. Square root of u is u to the 1/2. By the power rule, f prime of u is 1/2 u to the half minus 1, which is 1/2 u to the minus 1/2. So dy dx, which is f prime of g of x, g prime of x, See, what is f prime? This is the same as 1 over 2 times the square root of u. This is 1 over 2 times the square root of g of x times g prime of x, which is 10x. And see, this is 10 over 2, so I have x. 10 over 2 is 5 over the square root of g of x over the square root of 5x squared plus 1. Right? Any questions about this? Okay, so here's one more, which I would like you to do before I try to do it. Suppose I want to find the derivative, let me change the variable to t, of the function 5t squared over 3t squared plus 2 all cubed. So spend a minute, and the first step is to decompose this into the composite of two simpler functions that you would know how to differentiate. Let me just pause for a second while you do that. What do you get? So what we have here is, first of all, the cube of something. So it's natural to say, well, what are we cubing? We're cubing the function g of t equal 5t squared over 3 squared plus 2. And we're taking this function and cubing it. So if we let f of u be equal to u cubed, this is exactly the composite, the derivative of the composite function f of g of t. This means cube g of t, this is g of t, this is what we get. So we need to know the derivatives of these. So by the chain rule, this is f prime evaluated at g of t times g prime of t. F prime of t is very simple, or f prime of u. If f of u is u cubed, f prime of u is 3u squared. So this is going to be 3 g of t squared times the derivative of g prime of t. For that, we use the quotient rule. This is g of t, so g prime of t, we square the denominator, 3t squared plus 2 squared. It's the derivative of the numerator, which is 10t, times the denominator, minus the numerator, times the derivative of the denominator. So what we get is something over 3t squared plus 2 squared. This is 30t cubed, and here I have minus 32 cubed, plus 2 times 10t plus 20t. That's what goes in here. 20t over 3t squared plus 2 squared. What was g of t? That's 3 g of t, 5t squared squared over 3t squared plus 2 squared times 20t over 3t squared plus 2 squared. So I get something with the denominator is 3t squared plus 2 to the 4th, this square times this squared. And the numerator, I have 3 times 20t, which is 60t, times 25 t to the fourth times t to the fifth. So 60 times 25 is 1500. So if you do the arithmetic, the derivative of this function, it's the cube of a rational function, is 1500 t to the fifth over 3t squared plus 2 raised to the fourth power. That's something we'll give a star to. I'm trying to pick examples in the text, so when you're studying at home and reading the book, you can see what's going on. All right. Any questions about this? All right. A special case is when we have a function g of x, which we're raising to the power of p, and we want to differentiate it. So we're taking g of x and raising it to the power of p. If we think of u as this function g of x, we're looking at a function u to the p. So if I take the function f of u to be u to the p, this is the composite of f of g of x. F of g of x means g of x raised to the pth power. So by the chain rule, this is f prime of g of x, g prime of x.
We deleted it.
Now, if f of u is u to the p, f prime of u is
Mhm.
p u to the p minus 1. So this is going to be p g of x to the power p minus 1 times g of x. And this is a very important special case of the chain rule. It's the chain rule for powers that says if you have g of x to the power of p, the derivative is this. So if you have, for example, the function tangent x plus 10 raised to the 21st power, what's the derivative of this? So this is something, this is my function g of x. So this is going to be p, and p is equal to 21. So I get 21 g of x to the 20th times g prime of x. That's 21. G of x is tangent x plus 10 raised to the 20th power. And what's g prime of x? The derivative of the tangent is secant squared. So that's the answer. All right. Okay. Let's look at a couple more examples. All right. So there's a lot of sort of technical ability you have to develop using the chain rule, which you only can do by practice. And if you haven't done the practice before the midterm, then you will not do well in the midterm because there are very few derivative problems in calculus that do not use the chain rule. Okay. All right. Sometimes you have more complicated composite functions. Suppose you have the function y is equal to the sine of the function e to the cosine x. So you can think of this, let's see, in the first step, let's say maybe g of x is e to the cosine x, and f of u is the sine of u. So f of g of x is the sine of e to the cosine x. So this is the composite of the functions f of g of x. So dy dx is f prime of g of x, g prime of x. So if f of x is sine u, f prime of u is cosine u. So this is going to be the cosine of g of x, that is the cosine of e to the cosine of x, times g prime of x. But this is g prime, and it's not clear what the derivative of that is, because g itself is a composite function. So if you have, so we have to apply the chain rule another time, a second time. We have g of x equal e to the cosine of x. This is like, I don't know, e to the v, where v is the cosine of x. So let me call this thing, well, I'll call this maybe s of x. And suppose I have, and I'm taking e to that. So if I take the function, let's call it, well, y equals e to the v, this is some function of v. So g of x equal e to the cosine x, this is a composite of the exponential function with the cosine of x. So g of x is equal to f of g of x. This is equal to f prime. So this is e to the cosine x. So g prime of x by the chain rule is, actually I should use it, let me call this h, and I'll call this L, say. So this is L of h of x. So this is L prime of h of x, h prime of x. L of v is e to the v, so this is just e to the h of x. And if h of x is the cosine, h prime of x is minus the sine. So this is e to the cosine of x times minus the sine of x. That's g prime of x. That's what we insert there. So we get the cosine of e to the cosine of x times minus e to the x sine of x, sine x, times e to the cosine of x. Let's see. Let me do this again because I want to do this correctly. So I have the function y equals the sine of e to the cosine of x. So I can think of this as the sine of g of x, where g of x is e to the cosine of x. And I can think of this, I can write this as f of g of x, where f of, let's call this u, f of u is equal to the sine of u. So this is a composite of the sine function with the function e to the cosine x. But I'm going to need the derivative of e to the cosine x. So if I have u is e to the cosine x, this is a composite of e to the, let me call it h of x, where h of x is cosine x, and maybe I can write this as L of h of x, where L of x, L of v is e to the v. So this function is a composite function. U is the e to the cosine x, that's L composed with h of x. So du dx, or g prime of x, is the derivative of L prime of v is e to the v. So this is e to the v. If h of x is cosine x, h prime of x is minus the sine of x, minus sine of x, which is minus e to the cosine x, sine of x. So dy dx is f prime of g of x, g prime of x. F prime of g of x, f of u is sine u, so f prime of u is cosine. So this is the cosine of g of x times g prime of x. Cosine of g of x is the cosine of e to the cosine of x. G prime of x is minus sine x e to the cosine of x. So we have a product of these three terms, minus sine x e to the cosine of x, and the cosine of e to the cosine of x. So that somewhat complicated mess is the answer.
Professor, quick question.
Yes.
It's not about this, it's about the midterms. Is there any way we could get like a sample test so we could practice those before the
Oh, yeah.
midterm?
I mean, midterm is still a month away almost, but there will be a practice exam that I give you. But I mean, it's basically going to be, here's a list of functions, find the derivatives. Here's the function, find the tangent line at a point, that sort of thing. It'll be just like what we've been doing in class.
All right, thank you.
Yeah. Okay, let's do another example. Suppose I have the function x squared times the square root of x squared plus 1. And I want to find the derivative. So this is, again, a complicated function, but if you look at it, first of all, it's a product of two functions. So if I use the product rule here, I get the derivative of x squared, which is 2x times x squared plus 1, plus x squared times the derivative of the square root of x squared plus 1. So I have to figure this out. And for this, I use the chain rule. The derivative of the square root of x squared plus 1 That's the derivative with respect to x of x squared plus 1 to the power of half. So I can use the power rule for here. This raised to a power, this is going to be 1/2 x squared plus 1 to the minus a half times the derivative of x squared plus 1, which is 2x. Let's see, the 2's cancel. So this is x over the square root of x squared plus 1. So if I plug that into this, I get what? I get 2x times the square root of x squared plus 1 plus x squared times this, that's x cubed, over the square root of x squared plus 1. And if I want to put this over a common denominator, I multiply this by square root of x squared plus 1, I get 2x times x squared plus 1 plus x cubed. This is 2x cubed plus x cubed plus 2x. I get 3x cubed plus 2x over the square root of x squared plus 1. So that's the answer. Okay. Any questions about this? All right. Let's try an interesting problem. I'm looking at the textbook right now, and on page 198, number 82, is a problem involving cell populations. So you have cells growing in a petri dish, and the population at time t is given by the following function: 1600 over 1 plus 7 e to the minus 0.02t for t greater than or equal to 0. So this is a mathematical model for the number of cells in the cell culture after t days. And the first problem is to graph it. So if we look at this, of course, one thing we see is this is always positive. And what is the initial population? At time 0, p of 0 is 1600 over 1 plus 7e. When t is 0, this exponent is 0. And e to the 0 is 1. So this is 1600 over 1 plus 7, or 1600 over 8, which is 200. So the initial population at time 0 is 200. What happens as t goes to infinity, as time increases? So this function, e to the minus 0.00, this function, this is always positive. And if t gets bigger, e to the minus this is decreasing. So this is a positive number, which is getting smaller. When the denominator gets smaller, your fraction is getting bigger. So this population is increasing. And as t goes to infinity, though, this is approaching e to the minus this is going to 0. So as t goes to infinity, p of t approaches 1600 over 1 plus 7 times 0, or So this is increasing and it's getting closer and closer to a maximum population of 1,600. So the graph of this function looks something like this. So this is part A. Part B asks for the average growth during the first 10 days. That's just equal to the population after 10 days minus the initial population divided by 10. That's the average population. So that's equal to 1/10 of what? When t is equal to 10, 0.02 times 10, let me just write this out for a second. 0 over 1,600 over 1 plus 7e to the minus 0.02 times 10 is 0.2. Is that? Minus the population at time 0, which is 200. Well, for that, you need a computer or a calculator. So I will take out my calculator and try to calculate this. So I have 1,600 divided by 1 plus 7 times e to the power minus 0.2 . Let's see. Actually, it's easier for me to use Maple. So let me just, for a moment, switch to Maple and do this calculation. So I hope you're seeing the screen right now. So what I wanted to calculate was, so I have a function, let me just write down it's a function, P. Oops. So P is the function, T goes to 1,600 divided by 1 plus 7 times exp is how you do the exponential function in Maple, exp to the minus 0.02 times t. Oops. We got a parenthesis there. There we are. So that's my function. And if I want to plot P of t, say t goes from 0 to 10. Ooh, that's interesting. That's what it looks like, right? But I'm going to graph it to 100. Huh, that's more interesting, perhaps. I want the axis here. Okay, so that's what our function starts to look like. And the average over the first 10 days is P of 10 minus P of 0 over 10. That's the average growth. Actually, I'm curious about something. So P of 10 is that, and P of 0 is 200. So the population increased by 37.7 over 10 days, divided by 10 gives us the average, 3.77. Okay. Let's look at this over a bigger period of time. Let's say over the first 500. Oh, wow. So this thing is increasing, and then it seems to tail off. Well, we saw when we analyzed this by hand that there was a horizontal asymptote at 1600. Let me put that in. Okay. So we start out at time 0. After about a year, it slows down. I mean, it's increasing, then it slows down. And it's approaching 1600 asymptotically. Where is the growth fastest? It looks like it's fastest somewhere around there. All right, that's where it looks like it's fastest. This computes the rate of increase of this population. Well, that's just the derivative of the function p at time t. That's the derivative. What does that look like? Let me plot this. Suppose I plot d of p of t So that's what this is the rate of increase in the population. So let me this I don't need. Let me just erase that. So here, I don't need any of this at the moment. So here is the population growth. At time 0, there are 200 bacteria. The number increases after about a year, it's this much, but see, it's increasing faster and faster, and then more and more slowly, but it's always increasing. And this is the speed, the velocity of the population growth. It's going faster and faster and faster. It hits a maximum rate of growth after about 10 or 20 days. And then the growth decreases, but it's always positive. It's always increasing, but it's increasing more and more slowly. So this is what my population curve looks like. And this is the rate of increase of the population. It's very, very interesting. What's the maximum value the fastest that it's growing. So, so remember D of P of T oops. Sorry, that's my D of P of T. That is the derivative. And you have a maximum where the derivative is 0. Suppose I say F solve this equation. For T. This says, find where the derivative of the population growth is 0. And that's at, that's weird. Let's look for a positive solution. That doesn't make any sense. So here are the D of P of T. So this is, when does this curve have a maximum? Oh, we have to find where the derivative of the derivative is 0, right? So how do I find the second derivative? I can do it in several ways. I can do D at 2. So this is the second derivative. It's a little bit complicated, but I don't really need to know that. I just need to solve the equation. When is the second derivative equal to 0? Solve that for T. After 97 days. So let me call this number, I just call it Z for the moment. So Z is this number. So that's the time where this rate of increase is maximum right here. So at 97.295 days, the population is increasing most rapidly. And what is the population at that time? The population at that time is P of Z. 800. Wow. Very interesting. So this population at the time of greatest increase, the population is up to 800. So right there is where the population is the greatest. It's exactly half of the maximum. That's kind of interesting. Okay. All right, so that is using just a little bit of calculus to understand something about population growth of many species. They grow rapidly, but they don't keep growing faster and faster. At some point, there's a competition for resources and intra-species rivalry, and the rate of growth declines. Any questions about this? All right, good. Then we're done for today, and I remind you that today is Tuesday to the rest of the world, but in CUNY today is Monday, but tomorrow is Wednesday to us and to the world. So we meet again tomorrow, same time, same place. Any questions before we quit for the day? Okay.
Yeah, I just have a couple of questions. It's not necessarily about the material itself.
Yeah.
I just have a question. So, like, if you were a student and you were taking this course, like, what are the things that you would do in order to be most successful? Like, if you were taking this specific course,
Solve as
like,
many
taught by-
problems as possible.
I'm sorry?
Solve as many problems as possible in every section. That is, especially for the midterm, what we're learning are techniques of differentiation. That's the core. It's not the only thing, but that's the core part of the course. So you have to learn how to calculate derivatives of many functions by hand. And I wouldn't just use the online homework sets. I would, or use them, but always use them with a lot of paper and pencil at hand. So, because when you have to take the exam, you're not going to have a computer, you're not going to have a calculator. All you're going to have is the test paper in front of you, a blank page, and you have to solve the problem. So, and what you should do really is start with problems that are solved online or on the text. So, and just go through the method of solution step by step to make sure you understand what's involved.
Yeah.
Then do problems, and the computer, the Pearson system online, tells you when you make a mistake. So you don't want to like try things at random until you get the right answer. You really want to make sure you do get the right answer. It's not like a course in interpreting a play of Shakespeare where there are many interpretations. Typically, if you're given a function and you have to find the derivative, there's only one derivative. So the more time you put in solving problems at home, that's the better you will do. That's really what you have to do. You want to understand the concept of the derivative, that's fundamental. And then you need to be able to calculate the derivative.
I guess I'm just kind of having an issue because like I'm used to like being taught like processes before we get to the examples part, and I feel like every time I come to class, like I miss the actual lecture part, and we're always doing examples, so it kind of just confuses me. Like, am I supposed to learn it?
So you have something like the product rule, right? The derivative of f of x times g of x dx. So I proved that this is equal to f prime of x g of x plus f of x g prime of x. I gave a proof of this. However, in this course and in second semester calculus, that is in beginning courses in math and calculus, the most important thing, I wouldn't say that, but the essential thing is that you can actually solve problems, find the derivatives. If I asked you to prove this or something like this in an exam, that's actually, that's something that would be great if you could do that. But for most people at this stage in their mathematical education, that is still something of a stretch, and you don't start to see proofs until you are in your fourth or fifth semester of mathematics classes. At this point, you have to be able to solve the problems. Even when you're given proofs, you still have to solve problems. So, as I say, this is a class to a great extent, not completely, but to a large extent, it's a class where you, in technique, and skills, you have to learn how to compute derivatives. Right? It's like when you're still learning how to write, you're not asked to write a short story. That comes later. So this is like learning arithmetic. You can't do math without arithmetic. You can't do math without being able to compute a derivative. The only thing that's 100% certain is you haven't understood them. If you can't solve the problem, then you don't understand the material. You might be able to solve the problem without understanding the material because you've learned the techniques. But if you can't solve the problem, then but anyway, solving the problem is what you have to do. That's kind of simple, actually. So.
Yeah, I understand. I've gone to the tutoring like math sessions before. Like I don't remember where the room is, but I went there before, and I guess like the problem that I was having even there was having to explain to him the things that I don't really understand. And it's hard to do that because in class, there are no words, like it's just examples. So it's like when I get there, all I have to show him is a paper of examples. And like, I can't really tell
Well,
him what
what
I
kind of
don't
words are you looking for?
like. You know, I don't
I mean,
know if
here's the
that's how you
product.
know.
I mean, it says the derivative of the product of two functions is the product of the first times the second plus the first times the derivative of the second. I mean, so there it is in words, but that's exactly what this formula expresses.
Okay, thank you.
I mean, you do have to get used to mathematical talk, which is it's a language in its own right. Right. Any other questions, comments? Okay, be well. I'll see you tomorrow. Bye.